This is third lecture of module 1. So, in this lecture we will review tensor algebra and we will understand some of the operations required to understand this course properly, the tensor operations. So, in the last class we have introduced the tensors and what is zeroth order tensor, what is first order tensor, what is second order tensor, and probably I have also told what is the fourth order tensor. So, for instance, we have also seen the third order tensor, that is the Levi-Civita symbol or permutation symbol. So, in this lecture we will review some of the tensor algebra, which we have already seen in the last class. So, we will see it in little more detail. So, we will start with a very simple thing. So, we will start with vector algebra. So, as we have seen we have introduced the initial notations. So, any two vector A and B can be written in this form, and then these the geometric interpretation of vector sum and vector subtraction is this. So, which is a which is very well known to us from our basic vector knowledge. So, in a component form we know how to write it. So, C1, C2, C3, if it is the sum, then it is component wise sum. A1, A2, A3 is added with B1, B2, B3. So, A1 plus B1, A2 plus B2 and A3 plus B3. So, similarly, subtraction is also the sum of negative of B1 with A1 with A. So, so A1 minus B1, A2 minus B2, A3 minus B3 and so on. So, in initial notation, this is written in a very compact form. This is Ci is Ai plus Bi, Di is Ai minus Bi. So, this notation implied that this is the sum of two vectors A and B. So, this we know it from our last lecture. Now, similarly, we have introduced the dot product. So, geometric interpretation of dot product is, all of us know, if the angle between two vectors are theta, then dot product is nothing but the magnitude of u, magnitude of v, and then cos of theta. So, in a essentially the dot product determines the magnitude of the vector. So, then angle between the vector can also be determined from the dot product, because we know the expression for dot product. So, but if you do vector in a initial notation, the dot product in initial notation, that also we have seen in the last class. So, which is ui uj vj. So, now here to do the dot product, we need to take the dot product between two basis vector Ei and Ej, which is we have seen the delta Ij, because Ei dot Ej will be 1 only when I equals to j. So, otherwise it is 0. So, if I not equals to j, then it is 0, this quantity will be 0. So, I can simply write this is ui vi or uj vj when I and j are same. So, this if we expand it, so e1 v1 plus e2 v2 and e3 v3. So, this becomes easy in writing with the initial notation. Now, if we similarly introduce cross product. So, cross product of a vector also you know, which represents this area. So, u cross v is mod of u plus mod of v, or the magnitude of u or magnitude of v is then sin theta, and this is a vector. So, u and v is orthogonal to both u and v, and the direction is given by the right hand corkscrew rule. So, this is very well established result from our basic vector knowledge. So, if you write u cross v, so this is the determinant of this u cross v, and if we write it in terms of Levi-Civita or permutation symbol, so if epsilon I j k is u j v k e I. So, this also we have seen in the previous lecture how to represent it through in a compact form through a Levi-Civita symbol. So, now this epsilon I j k or the epsilon is a third order tensor which has 27 components we have seen. So, among 27 components, 3 components are +1, 3 components are -1 and other components are 0, that we have seen in the last class. So, now once we able to write it in a very compact form, our proofs and our representation will be in a very compact form through the indicial notation. So, another thing we have seen in the last class, which is also the scalar triple product. So, it is very well known, the physical meaning of it, it represents the volume of the parallelopiped. So, this is already from our knowledge of basic vector algebra. So, if we want to do this will be dot. So, this if we want to do dot product between two vectors, that expression we know, and if one of the dot product is expressed in terms of cross product of other two vectors, that is v cross w, then this becomes u dot v cross w. So, now if we write it in a proper manner, so the u is represented u I E I, and then any two vector v and w is represented again with the third order tensor epsilon. So, which is epsilon p j k v j w k e p. And so, if we now these alls are scalars. So, these alls are scalars. So, we can take it out and then do the dot product operation between E I and E P. So, if we do this dot product operation, so as we know from our relations, these E I and E P will be 1 only when I and P becomes equal. So, this leads to delta I P, and then I can conveniently change the symbol, because delta I P I can write it 1 when I equals to P. So, I can just simply substitute here I j k and then V j w k. So, this P I am assuming it is equals to I. So, then only this expression will valid, otherwise this delta I p when I and P are different will be 0. So, finally, this quantity will be 0. So, this will be non-zero only when I equals to P. So, I can substitute conveniently A P equals to I. So, this leads to a compact notation, and this we have seen also in the last class. So, now we have also introduced what is tensors. So, here I will give another definition of a tensor. The tensor is an object which transform following a certain rule under coordinate change. So, if you have seen our basic definition of tensors, the tensors is a linear transformation which transform a some quantities to other same to another quantity. For instance, the second order tensor transform a vector space to another vector space. Similarly, we can for instance, the fourth order tensor. The fourth order tensor transforms a second order tensor to another second order tensor. So, just like we have introduced matrices or the square matrices or the matrix vector equations A x equals to b. So, if we just write A x equals to b. So, this is a second order tensor which transforms this vector x to vector b. So, if x vector belongs to a vector space and b belongs to another vector space, then we can say this vector A transforms one vector space to another vector space. So, we can view it, if you remember from our the solid mechanics knowledge, that coordinate transformation, which we have also briefly discussed in the last class, that when we transform from one coordinate to another coordinate, then we need to multiply a rotation matrix. So, how to calculate this rotation matrix also we know, because rotation matrix are composed of direction cosines between two coordinate system. For instance, this is a coordinate transformation example. If E1, E2 and E3 are initial coordinate system or the old coordinate system, and then if we rotate it arbitrarily with and the new coordinate system becomes E1 prime, E2 prime and E3 prime, and if there is a vector P, then how should I represent P? That is the object. So, and how the P will be in terms of E1, E2, E3 system and E1 prime, E2 and E3 prime system. So, now we need to define first how these E1 and E1 prime is related. So, if E1 and E1 prime from our basic definition of a tensor, we assume that E1 prime is transformed through a or EP transformed to a tensor EIP through this. Now, if we just pre-multiply with or post-multiply or take the dot product with the Ej, then we can simply prove that Ei prime dot Ej is Qij. The proof is very simple, because this will be delta Pj, and then delta Qip delta Pj will be when p equals to j, then Qij. So, similarly, we can write that E1 prime is Q11 E1, Q12 E2 and Q13 E3 and so on. So, this defines the component of rotation matrix. We will see through an example. So, but interestingly, one must notice that and one can prove from this that this determinant of this matrix Q, which is Qij, component wise it is Qij, is actually the plus minus 1. So, this kind of transformation is known as the orthogonal transformation. So, this matrix Q belongs to orthogonal set of orthogonal matrices. So, this is an orthogonal transformation. So, it is better to remember this thing, and we have also seen this earlier in our coordinate transformation part. Now, our will just proceed very simple thing. If I want to transform a scalar, so scalar is a quantity which has only magnitude, there is no direction. So, scalar can be transformed to any coordinate system and which does not affect. So, this is that is why we say the scalar is a zeroth order tensor. So, scalar will not change under the coordinate transformation. Now, simply the vector, if we just write it in this two different coordinate system Ai Ei and Ai prime Ei prime. So, it will be like this. So, this and how Ei and Ei prime is related, that we know from the previous slide. So, we can just conveniently transform the vectors from one coordinate system to another coordinate system. Now, if we really want to derive that, then it is very simple. P I can write Ai Ei, and P also we can write in Ai prime Ei prime. So, if we take dot product, then this proof is very simple. Actually, if we take dot product with the Ej prime, then it will be Aij A prime j, and then we can relate Ei and Ej prime with the Q ji, and so the component wise how it will look, it will be derived from the it will be obtained from the q ij components. So, that we have seen in the previous class. So, finally, you see this components of rotation matrix is multiplied only once here, because vector is one directional quantity. So, it has one direction. So, that is why we say it is a first order tensor. So, similarly, if we want to transform a tensor, how it will look. So, tensor transformation we will see it little more detail. So, if I want to write ai prime with the AP quantity, that is prime coordinate system, and the non prime coordinate system, it is related with that. So, similarly B prime Bj prime is related to this. This we have learned from the previous slide. So, now if I want to transform the tensor obtained by these two vectors, then ai prime ai prime and bj prime, I can just simply multiply these quantities here, and we have to keep in mind that this is 2 times. So, now if I write this, if I say these ai prime and bj prime are c ij prime, then this looks like this. So, this is a transformation formula for the second order tensor. Now, if you see carefully this when it becomes a tensor, so it has two times it is multiplied with the component of the orthogonal tensor q. Now, this c I j, how it looks, so that also we have defined in the last class. So, it is the dyadic product which is a I b j. Now, this is in a tensorial notation, this is in the indicial notation. So, it is known as the dyadic product, or sometimes it is also known as the tensor product. So, now we know how to transform a tensor to another tensor under coordinate transformation. So, the important thing to remember here that since the second order tensor have two directional part. So, it has two direction. For instance, the stress tensor represent how you always write sigma xy, sigma xx like this. So, two subscript you always write. One subscript is for the direction of normal, another subscript is for the direction on which the stress is working. So, it has a two direction. So, since it has a two direction, it will be two times the orthogonal component of the orthogonal matrix will be multiplied. So, this as we should remember. Now, if we the dyadic product that we have introduced, we can write it very proper manner. So, this dyadic product we can write it the vector ai ei tensor product, or dyadic product bj ej. So, finally, these ai and bj is a scalar. So, I take it out, and then the tensor product is between these two unit vectors. So, if I expand it, this is in indicial notation, this is in tensorial notation. So, if I just expand it, so E1 tensor product E1 and then so on, right. So, if I write it in a matrix form in the these quantities, the components of C, so C I j will look like this. So, A1 B1 to A3 B2, right. So, I think this will be A3 B3, right. So, this C is a second order tensor formed by the dyadic product of vectors of A and P. So, how these so what we have learned? We have learned how to transform scalars, how to transform vectors, and how to transform second order tensor. Now, we need to understand how the higher order tensors transforms, because we will not use much of the higher order tensor in this course, but it is better to know how to transform the higher order tensors. So, similarly, for a third order tensor, the components of Q will be multiplied 3 times, because it has 3 directional part. And for the fourth order tensor, it will have the 4 directional part. So, in this way we can transform efficiently the third order and fourth order tensors. So, let us see what type of coordinate transformation through an example. For instance, if the A is a second order tensor and B is a vector, we want to transform it. So, first let us rotate this coordinate system x1, x2 and x3 with in the xy x1 x2 plane, we rotate it 45 degree. So, now our first job is to find out the components of Q, and components of Q, if I write it in this form, in a matrix form. So, E1 prime dot E1, so which is actually the x1 and the cos of angle between x1 and x1 prime, which is 45 degree. So, cos 45. So, similarly, E2 prime dot E1, that means the x1 x2 prime and x1. So, which will be again 35 degree, because this is 90 minus 45. So, this is 45, and then this 90 will be added. So, 135 degree. So, 45 plus 135 degree. So, the 90 plus 45 degree. So, this becomes 135 degree. So, similarly, you see this becomes cos 135 degree. So, now if we see that what is E3 prime dot E3, which will be because E3 prime and E3 is essentially here x3, the angle between x3 and x3 prime. So, since we have rotated 1-2 plane, so x3 it does not change, x3 and x3 prime coincides. So, this angle between this is 0. So, actually this is a 2D rotation. So, one important thing here just for your information, that if you do a 3D arbitrary rotation, this is not commutative. So, this information we can keep in mind. So, this becomes our rotation matrix. Now, once we find out the rotation matrix, our all quantities we can transform from x1, x2, x3 system to x1 prime, x2 prime, x3 prime coordinate system. So, how it looks like? So, now this is the tensor. So, ai prime ij is qip, qjq, apq. Now, this if we write in a tensorial form, so it looks like this. So, we can also prove that. So, if I take the ijth component of a prime, so which I can write it in this form q a I q, that is we take these tensors first and write its iqth component and transpose of q, that is qj's component. Right. So, if I now again write q and a in tensorial form, in initial form. So, I introduce p in this index. So, qip and apq, and then qj. So, if I write it now, you see this is qip, qjq, apq. So, which is similar to this. So, the initial form is this, and the tensorial form is this. So, this tensorial form is important because we do not have to keep in mind in this initial form, but we should always able to given a tensorial form, we should always able to write the initial form, or given it initial form, we should always able to write the tensorial form. So, now finally, once we know this form, then a prime I can just simply write q a and q transpose, and this a prime becomes this. So, this is a example of how we can transform the coordinates. How we can transform a tensor in a rotation of the coordinate system. Now, similarly, the vector is again b I prime. We can write q and b. This is a very well known result. So, we just multiply with the rotation matrix and this becomes the vector in the prime coordinate system. So, now some examples of the tensor. So, for what we have learned is the scalar is a zeroth order tensor. So, which I have already discussed in the last class. So, density is a scalar. So, it has no direction. First order tensor, traction vector. So, traction sometimes we probably those who have done solid mechanics, traction probably they have heard. So, traction vector, velocity, these are the first order tensor because these are the vectors. So, second order tensor is trace is a second order tensor, strain is a second order tensor because it has two subscript. So, the in the description also we write it in two subscript. So, this is very important to know. So, stress strain is a second order tensor. Similarly, fourth order tensor, those who have I think all of us probably have heard this Hooke's law. So, this Hooke's law, when we use the elasticity matrix or the constitutive matrix, this is actually a fourth order tensor. So, we will see it in detail how this fourth order tensor comes and how this we can write this fourth order tensor in a matrix form. This we will see it in a later part, but later part of this course. But it is better to know right now that this constitutive matrix is a fourth order tensor. So, you see here also we can verify the definition of the tensor. So, this C is actually the this C is a fourth order tensor which transform a second order tensor strain epsilon to another second order tensor which is a stress. So, in a better way which transforms the fourth order transforms a second order tensorial space to another second order tensorial space. So, in this way we can define any order of tensor. So, now, if we see examples of tensors, for instance, the tractions, the traction vector, we can write the Cauchy's law of if you have gone through the solid mechanics. So, which is sigma n. So, n is the normal. So, if I write it in a initial notation, T I is sigma I j n j. Now, so, as I was discussing in the last class that a second order tensor can be thought of a linear mapping from one vector to another vector. So, essentially it is a linear transformation. So, why this word linear means? The linear means the basic definition of a it comes from the basic definition of a linear function. So, if I now use two arbitrary scalar a and b and two arbitrary vector n and m, and if I post multiply with this tensor sigma, then my result should be a sigma n plus b sigma n. So, if this property is satisfied and if I multiply this alpha with n and then pre-multiply alpha with the n and then that vector if I post multiply with the sigma, then it becomes equal to the alpha sigma n. So, if these two properties are satisfied, then we say this tensor is a linear tensor, linear function or linear tensor. So, this linear mapping we say. So, this actually the transformation is linear. So, the reason for linearity is these two property. So, it satisfies these two property. Now, once we know what is tensor and its transformation, then we can understand the transpose of a tensor. So, transpose of a tensor, second order tensor is very similar to transpose of a matrix, a square matrix. So, Sij is actually Sij transpose is actually Sji. So, in the last class we have also seen what is the skew and skew symmetric and symmetric part of a tensor, second order tensor. As we have discussed in the last class that any matrix can be written in terms of a summation of a symmetric tensor and skew symmetric tensor. So, which can be written is that in this way, if in this expression if I add half of S transpose and deduct half of X transpose and rearrange it in properly. So, this is the symmetric part of the tensor and this is the skew symmetric part of the tensor. So, this in a initial form looks like this, that we have seen in the last class. So, now we can have an example. Before that, there is a trace of a tensor. Trace of a tensor is also we have seen, which is the summation of all diagonal element or summation of diagonal components of the matrix, second order tensor S. So, which is trace of S is Sii in indicial notation. Another important component is that deviatoric component of a tensor and spherical or volumetric component of the tensor. So, if S is a deviatoric component, the definition is S is deviatoric if trace of S is 0. So, what we do is essentially we deduct 1/3 of trace of S and I with the S and then add this 1/3 of trace of S. So, this components becomes deviatoric and this components becomes spherical. So, this we will see through an example also. So, suppose this is a second order tensor A and then trace of A is this, which is the A of II. So, the 1, 2 and 0, which is 3, and then symmetric part of the tensor we can write it S or A half of A plus A transpose. So, A transpose is this. So, we can just add it. So, this is a symmetric part of the tensor. If you see why it is symmetric, the off diagonal elements are same. So, skew symmetric part of the tensor. So, this has to be the negative. This is minus actually. So, this is minus. So, if I do this half of A transpose minus A minus A transpose, then you will see that this is a symmetric part of the tensor. Why it is symmetric? Because off diagonal elements are negative to this, that is Aij or the skew of Aij, skew of Aij is Aij equals to minus of Aji, and all the diagonal component is actually the 0, all the diagonals are 0. So, this is an example of a tensor. We can write it in a skew and skew symmetric and symmetric form. Now, what is the spherical component of the tensor? So, if I write we know what is trace. So, 1/3 of trace of A into I, see trace is a scalar quantity and spherical part of the tensor is a tensorial quantity. So, we have to multiply with the identity tensor and which becomes an identity tensor. Now, deviatoric part is essentially A minus 1/3 trace of Ai. So, if we just deduct this component, this becomes the deviatoric component of the tensor A. Now, if you look carefully, the trace of this deviatoric component is 0. So, it is not necessarily all the component, all the diagonal component of the tensor is 0, but summation, that is the trace of deviatoric of A is 0, 1 minus 1 is 0 actually. So, trace of deviatoric of A is 0. So, this we can remember. Now, the important product for the tensor we will be using most is the product of tensor. That is, if we multiply two tensor, how it will look. So, we have seen if we multiply two vectors, what will happen, like dot product, cross product and the dyadic product or the tensor product. Now, if we multiply product of these two tensor s and t and then I j, then it is simply s of I k t of k I. So, this is known as the inner product of the tensor. So, this can be written in the tensorial format in this form. So, this is the contraction sign, or sometimes this is known as the contraction operator. So, S contraction T is essentially trace of S transpose E, S transpose T. So, which I can write in a proper manner S I j T I j. Now, the magnitude of the tensor, for instance, the magnitude of the matrix, if we write it is the inner product of two matrix and root over of that, like the vector. So, S contraction S and root over of that. So, if you look carefully, since trace is a scalar quantity, trace is a scalar quantity, this quantity is actually the scalar. So, now for example, if you have seen in a solid mechanics this energy expression, then sigma contraction d of epsilon, which is essentially sigma I j d of epsilon I j, and if we write it in this, if we expand it the initial notation, then it becomes a scalar quantity. So, the important thing here is the inner product of a tensor is a scalar quantity. So, we need this in our relation. So, we will be using this quantity often. So, it is so the new product of two tensor we have learned in this class is the inner product of two tensor, which is trace. So, trace operator is in that sense is a very important operator. Okay. So, here we stop today, and in the next class or next lecture we will start with the tensor calculus.